All right, sorry for being late. So, second take on motion. So, in the next few minutes, we'll be looking at one fundamental aspect of video, which is how you track pixels in time. Okay, so how do you find what the motion of each object works? So, let's step back a bit and realize, okay, we're working in 2D because pictures are 2D, but really the word is 3D, okay? And so, are you doing the computer vision course, any of you? No? All right. So anyway, so it's a classic computer vision problem. So how do you project 3D objects onto your picture, and how do you understand how do you do perspective in pictures, right? So the simplest example of that is, model for that is a pinhole camera, and that just works fine for 99% of your problems. So this is kind of the basic geometry here. You have an object that lives in 3D, and this object gets projected onto a plane, which is your sensor, if you want. And you have this virtual point here, which is the optical center of your camera. So imagine if you had a pinhole camera. The pinhole camera is just a box, and you just have a small hole, tiny, like a point. And what happens is that all the lights gets all the lights will go around here. Let's say this is the hole, and it gets projected back onto a screen here, okay? And that screen here, if you want, that's this screen here as well. So that's a simple model, and now there's a lot of maths behind that and after that, and especially if you want to find all the parameters of your camera, because your camera has a number of parameters. But you see here, one of the fundamental parameters is the focal length. Okay, so the distance from your optical center, where all the rays of light converge, and your screen, where you actually see everything in 2D. So that's the focal distance, and if you use simple triangular identities, I'm trying to make that a tiny bit bigger. You get a simple relationship between all these distances, and so if you look at the distance x1 here, which is your pixel, and x1, which is your 3D representation coordinates, then you have all these nice identities holding up, and you can actually work out simply the relationship between the 3D and the 2D. Now, as I said, in real life, things are a bit more complicated. Because you might have distortion, you have all sorts of things going on in your lens and so on. And it's only kind of recently, I'd say in the last 15 years or so, that, well, that's 10 years, really, 15 years, 10 years, that most of the mathematics of all that have been kind of sorted. So now it's quite well understood, and if you have a sequence or different images taken from different angles, we know how to recompute all the elements. We know where to find the coordinates of where the camera was, or where the focal length of the camera was, and so on. So that is, there's a lot of mathematics involved there to do that correctly. So, right, at our level, we don't really see 3D motion, and in case of compression, we're not that interested in going as far as understanding what the exact location of the 3 points are. But just something good to know that the real world is 3D and not 2D. So when you look back at what kind of transformation you have in 2D, there is a number of parametric transformation that comes to mind. So this on the top left here, you would have translation. So this is the position in the two frames, so the solid square is the actual object on the frame, and the dotted one is the location in the next or previous frame. So here in this case, you have translation, so just the object, which is a square in this case, has just moved as a translation. You have rotation, zoom, and the last one is called perspective transformation, and it undergoes homography. And this transformation is basically the most useful one, I suppose. That's the one that tells you how, if you had a 2D planes in 3D, so a surface in 3D, like say a wall, for instance, if you turn your camera by a bit, you know, what is the transformation of that wall? How does it look like after moving your camera? And this is what you get. Okay, you get the perspective transformation, which involves 9 parameters, 7 parameters. So anyway, so that's what you get. Okay, different transformations. The complexity that when you use to model what you see in 2D really depends on your assumption about what's going on in the scene. But at a fundamental level, really what's going on is just a warp. Okay, so your pixel so this is your frame. Okay, so I of n is the intensity image at frame n, and x in bold like this is just the 2D, the pixel coordinates. Okay, that will be x and y. So we say that if you have 2 frames, so n and k, the relationship between the two is we say, well, the value obtained as some coordinate is the same as the one shifted by some offset d. Okay, so this displacement is the information we're trying to recover. Okay, in real life, you would have like at least one displacement per pixel. So we're looking at what pixel has moved to where, and that might change from pixel to pixel. So that's why you would have we index that by the actual locations where you're at. All right, so that's the most generic model. Of course, things don't go very well. This model actually is only 80% correct, let's say, in practice. Okay, so the first problem you will have, and it's very frequent, is that luminance and color will change. There's plenty of reasons for that. The most common one would be that the camera has some settings to auto-adjust for the color balance or the brightness and so on. Okay, and so when you move the camera or over time, these settings might change, and therefore you will have slight variation. Other problems would be the lights you have. They flicker at 50 hertz. Depending on which variations, what your frame rate, acquisition frame rate is, the light will change. Okay, so you get flicker. The sun might change. Well, the clouds might change and so on. Somebody might open a door. So you will see very frequently and very abruptly things. The brightness might change from frame to frame, and not only the brightness, but the color cast as well. So it's called the illuminance. You would think naively that white is 255, 255, 255. Right? You would take the, but sometimes it's not. Okay, so sometimes here you have maybe a bit of a, I don't know, say a yellow cast. So maybe actually what you see here is not white but yellow. Right? Your brain does a lot of processing to make you think it's white, but when you look at the actual value of the pixel, you'll find maybe it's yellow, or maybe green, or maybe blue. And that might change as well from frame to frame quite a lot. So this is something that is tricky to do, to fix properly, but not impossible. Occlusions, okay, is a bigger problem. Is that, well, there's different cases, right? So but basically the object disappears, okay? So the pixel you're looking at actually disappears. So it shouldn't be visible anymore. So it's like, if you had my hand, if you had the other hand, it goes under the other one, behind it, you lose track of it, and you don't know where it should go to. So the idea to say that every single pixel originates from somewhere it's not necessarily true anymore because some pixels disappear and some pixels will appear. You can just think of what happens at the edge of the frame. Pixels, there's motion, the pixels will disappear. What do you do? The fourth one is the aperture problem, which is something we'll look into more detail, but which is basically, what if you have a white wall with no texture on it, and this is the only thing you're looking at? Or if you just look at the sky and there's no clouds, how do you know if the camera is moving or not? It's probably not possible. So anyway, there's all sorts of consideration, and then you have to think of the complexity of the model you're looking at. Are you looking for translation, rotation, and so on? And depending on how much problem you have above here, then probably you want to go for simpler models. Okay, so the reasoning is like the simpler the model is you have for the motion, then the simpler it is to estimate things. To finish problems you might have, lens distortion. Now, I talked about the pinhole camera model. Yes? Are you talking about the motion of the camera or the motion of the... Both. To some extent, okay, so if you rework in 3D, you can derive what the motion of the camera is. But say here we just look at the 2D, just at the first level. Okay, we don't go 3D. We look at the first level. If things don't move, well, it's kind of hard for you to know whether you're moving or the things are moving, right? The last 2 points, so lens distortion, it's a real problem that the pinhole camera model I talked about is a theoretical model. In reality, you have lenses, and lenses, they distort. They're not perfect. They distort the geometry of the light. So therefore, the pinhole model I talked about is not true, and what might have been a simple translation becomes something weird, okay? Because you distort. Like what happens at the bottom left is not the same as what happens in the center of your lens. Okay, so think GoPro. Okay, if you've all seen GoPro footage, they look kind of weird. You have this fisheye effect where the things on the side are not quite as straight. This is what I'm talking about, like all the assumptions you have kind of fall apart. And the last one is, a classic one is grain and noise, which is that even to this day and age, even on the most modern cameras, the most expensive ones, you still get grain and noise. Okay, so when you look at pixels, the value you get is not exactly that, it's something plus thermal noise. So for all these reasons, usually you have absolutely to say, well, there is some error term, and the error term is any of the above here, and it could be quite, it's not just Gaussian noise, okay, it's something way more complex. All right, so some terminology. This difference between this term here, so that's your frame, the value of the pixel current location. This is the motion compensated pixel. Okay, so you compensate for the motion in the next frame. So if you want, this is the prediction of what the pixel should be based on the motion information. So that should be called, it would be called motion compensated frame. And when you do the difference between what your current frame and the motion compensated frame is, then you get what's called the displaced frame difference. Okay, so the difference between your current frame and the displaced frame from the previous frame, for instance. So to think about it, okay, in simpler settings, okay, at least you want to minimize that, okay? That's the error you have, that's your epsilon term you had here. So what we want to do is to find the motion vectors that will minimize this difference, okay? So in other words, given a pixel, you want to find the most similar pixel in the next frame and say, if the two pixels are very similar, then probably my motion is correct. So this is how you formulate it. Okay, you just say you want to find the motion vector, the displacement that will minimize this error over all my pixels. So this is what we do in motion estimation. Now, this is totally incomplete, okay? We'll talk a bit later about why this is totally incomplete. But anyway, let's start with that, okay? So in compression, okay, we use something called block matching, right? Sorry, just a pause here. In terms of terminology, what we're talking about here, I would say that's called motion estimation. Different communities would say it's optical flow. Okay, both are the same term. Okay, so if you hear motion estimation or optical flow, both are exactly the same thing. So what we're talking here now about is one type of algorithm to do motion estimation called block matching. And that's the one used in the compression community. And that's probably the simplest one you can think of, okay? So basically, the idea is like it's a brute force approach. So you're going to take, not quite a pixel, because a pixel is not very useful, but you take a little block, and you're going to try to find the most similar block in the other frame, okay? And you say when you find the location in the other frame that has the best match, then you say, well, that's the displacement I have, and that is quite the best. So where am I here? Yes. So let's look at the graph here, okay? So this is that the best one we have? Okay, so this is the two frames. So you have this vague shaped object here, and this is in the next frame. And so frame n-1, frame n, and what you do is you look at tiled your image, split your image into different blocks, and you take a block, and now you want to know where this block was in the previous frame. Okay, so you take the same block size and just search for the best possible block. So first approach is to really have a brute force approach and to try every single possible location. So to know how good you are, because the metrics you would use, we could use any of the metrics, objective metrics we talked about. So the most robust one is probably the mean absolute error, and it's simple enough to compute, and it's quite a bit more robust than just mean square error. Okay, so we have the metric, we know what to do, and we just go ahead, and this is what happens. So this turns out to be quite a recurrent exam question. So it's to compute the number of that here actually. Maybe it's after. We'll see. It's to compute the number of operation it takes to do full block matching. Okay, full exhaustive block matching. So n is the size of your block size, and w is the search radius. Okay, so obviously you're going to bound how far you're going to look for that block. Okay, so typically you say I'm only going to look for blocks that are plus or minus some distance. Okay, and in that instance we are going to say that w is that distance. Okay. All right, and so to do a comparison, it's kind of, sorry, hang on a second, I'm trying to have to look at the slides of where, if we have some, that computation. No. We don't have that computation, sorry. No. Anyway, so that's kind of what's going on. So you have the grid. You're going to look within that grid. So that's 2w plus 1 squared possibilities of where, candidate positions you can be testing. And for each of the candidate positions, you'll be comparing the two blocks. And the two blocks are of size n by n. So you roughly have n squared operations to do the comparison. And you have roughly, say, 2w plus 1 squared candidates. So in total, you have n squared times 2w plus 1 squared. So times, so you have n squared times 2w plus 1 squared operations. Okay, so you square times squares. Okay, so you have the area of search times the area of your block.
Is it bracket 2w plus 1 plus bracket squared?
Yeah, but it depends how you define it. Okay, if your search region is w, the width of your search region is w, then it will be just w squared. Okay. So in the exams, you just have to define that correctly and be consistent. So, yeah. Anyway, so that's quite a simple stuff, but it basically tells you that very quickly during that's a problem with pictures and motion. Okay, that the number of operations you have is basically to the power of 4 almost of the number of pixels you're considering. And so therefore, you're very much limited. And even with today's technology, it's too consuming. You can't just brute force for every single position in your pixel, in your picture. So that's usually doesn't work very well. I think I have to go for that, but I think that might stop the recording. All right, so this is a classic test sequence from some time ago now. And you can see the test sequence because you have lots of complex motion going on, okay? So what you see on the left, okay, so first of all, most of the time you just work on grayscale images. It's not necessarily true anymore. The thing is with color, that the color information usually is the most unreliable one. And so therefore, if you want to do something that is a bit more robust, usually come down to grayscale. Anyway, what you see on the left is a previous frame, and on the right you have the current frame. And with the little yellow things you can see here, and I probably cannot zoom into it, no I cannot, are the motion vectors overlaid. Okay, so you had, for each 8x8 block, you have a little arrow, which is very small, but it tells you where it should go to, right? So if you see a point here, then you know that in the previous frame, this point here was actually at this location. Okay, so basically what you found, you had this little block, and you look at the whole search region, and you found a matching block, which was a few pixels on the left. You can see around the train that things are going the other way, so the motion vectors are pointing the other way, and around the ball things are a bit mad. Okay. Obviously, it's not perfect. Okay, if you look carefully, you'll see some motion vectors here that goes, a bit crazy, and especially here, this point goes all the way here, but what's happening is that at this point you have an occlusion. Okay, so the little ball of this pendulum is spinning, and at that location, basically what you observe in that frame and the previous frame just doesn't match anymore, and then you say search for something that doesn't exist in the other frame, and that could be anywhere, right? If you say search for a block that doesn't exist, then it will find something, but not what you were looking for. All right. So I think that plays. No, it doesn't play. Oh, yeah. So that's kind of, that's frame by frame So you can see that makes sense. So usually that's how you see motion estimation. You kind of play back and forth between the frames, and trying to align things, and usually trying to put a mouse or something along the tip of the where it should go to, and check whether it's indeed correct. All right, so this point here originates from no, right, it's too hard with PowerPoint. Okay, so here's an example of results. So this is a classic test sequence again, and this is again motion field. Now the results are not perfect, right? So this is just one of the techniques. In fact, motion estimation is very hard, and state of the art is still struggling quite a lot with motion in general. Sorry, I should have had some videos here, but all right. So how do you measure the performance of your estimates? Okay, so you have this technique trying to find the best possible shot, but then how do you go about knowing whether what you've done is correct or not? Well, one thing you can do is to look at this DFD, so the displaced frame difference. Okay, so remember what it is? That's the difference between the predicted frame from the motion and what you actually have at that point. And so you can do that over the entire picture, and you can compute the absolute difference between your prediction and your estimated work. Okay, but we'll see that's probably not the only metric you should have, because you could be very good and still the motion vectors could be very bad. All right, so on the left here, what you observe is a DFD, so the difference between your frame and the prediction. And what you have on the right is the difference without motion compensation. Okay, so look back at the equation. So here we just take two frames, consecutive frames, and we take the difference, and so mid gray is 0, and the usual stuff. Okay, on the right here you have the difference after compensation, and it makes sense, right? So this entire region, so that's a calendar sequence. Okay, so that's this sequence here. So coming back here, you can see that the entire region where you have a translation. Okay, it's a very simple motion, and each block is quite textured, and it'll be easy to find where this block came from in the other frame. So therefore, here you're doing a very good job, and everything is kind of cancelled out, like you have a very good prediction. Where things don't go well is here, so you have this crazy motion going on with the pendulum, and even at the train, at the boundary between the train and, you have two motions going on, motion from the train, motion from the background, and at the boundary here, you're not doing so good. Obviously, the simple reason for that is because you have a very simplistic idea model for the motion. What you say that your motion can be explained by translation over small blocks. Okay. Obviously, here it's more complicated because you should take into account the fact that every single pixel, there's a very fine boundary between the train and the background, and therefore, instead of looking at the block level, you should be looking really at the pixel level and be able to say where it should go into the next pixel. The error here, so the error here is mainly due to not so much the complexity of the motion, but more the complexity of the boundary between the two motions. The error here is due to the complexity of the motion, because the motion, it's a rotation and goes very fast, So it's just impossible to know what's going on, and you just have too much occlusion, and we just can't predict very well what's going on. Right, let's see if that works. Nine. Okay, so that doesn't work. Okay, well that was a video, I'll try to fix that later on, of the calendar to detail the DFD, the different scenarios. So obviously, okay, so this is a small graph in time of your error. So obviously, if you don't do any motion compensation, then the error, so that's the mean absolute error for the DFD. So the error in prediction is quite high, but if you apply motion compensation, then the error is a bit low, but not perfect, obviously. Right, so this is actually where the computations are for the number of Persians you have. So there's a number of tricks we can do, okay? I especially used, this is coming from a bit from the angle of compression here. So the point is, maybe you don't need to apply, so you know, how can you speed up the process, okay? Because as I said, doing full search, block matching is too hard. But you can do things, you know, you can check maybe locally the difference. I mean, motion doesn't happen all the time, okay? Most of the time, like the camera is static, for instance, there's nothing going on. So you don't need to look for where things have moved. So you could check locally, you know, is there actually any motion whatsoever? So you could say, locally, is my block similar to the previous block? And if that's the case, you test that as a first candidate. You say, is there any motion? You know, let's assume there is no motion. And you test it, and you see, well, if there is no motion, if the block at the previous frame at the same location looks the same, therefore there's probably no motion. So therefore, well, I don't compute anything. All right. So this is where we get here. This is the previous frame, the next frame, and the difference. So no motion compensation here, just a straight difference. And if you look at the absolute value of that difference, you can see that, you can clearly see everything in the background is, there's not much going on. The only thing where you have things happening is in these very specific regions happening at the borders, in the boundary of your objects. So maybe you don't need to compute the motion everywhere. Maybe you just need to compute the motion where you have motion, right? So that's kind of the idea here, okay? So you do this difference and apply some thresholds, and then you have a nice mask of where to go. Right, so this is the same idea. Can I play it? I cannot play the video. All right, so that probably just won't work. I'll try to update that for next week. So the next thing that people do, and that's actually used in in compression, is this hierarchical search. Okay, so the idea is like, this is the central location of your current pixel, and this is your grid, your search grid. Okay, so that's shown plus or minus. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so in this represents your grid of plus or minus 8 pixel search. Okay, so you'll be looking for 100 different locations, 16 squares, so 128 different locations, and you say, okay, this is, you know, my current location. This would mean like zero displacement. And so the simple hierarchical search would be, you first test these 9 locations at a step of 4. Okay, so you look plus or minus 4 in this 8 different positions, and you test for whether the block matches or not. And you look at the best matching block, and let's say this one. Okay, this one gives you the best one. So you know maybe this direction is better, but maybe it's not as good as it should be. So you know you're trying to refine from that position, and now you use that as a starting point, and you check for the 8 neighboring positions as well, and you compute the displaced frame difference at these 8 locations, and then you pick up which one is the best. And no, let's assume this one is the best. And you go on, and then you look at the pixels, nearby pixels, and see which one gives you the best. Okay, so you have a way of searching your space that will reduce by quite a lot your well, that kind of makes it linear basically. So that's actually what's used in motion estimation. The reason where it works is because you're looking at a big block, okay, and you're not just looking at one pixel. All right, so the other thing you can do is you can do the search at different scales, okay? So this is a typical thing you do in motion estimation or any image processing technique, is to work in a pyramid. It's called a Gaussian pyramid. This is the level 0 of your pyramid. This is the original picture. Okay, so you could do the processing at this scale, so with a, say, HD frame. But the idea is to say, well, maybe we should kickstart the algorithm at a downsampled version of that picture, right? Because the idea would be that maybe a displacement of, say, 32 pixels is quite a lot to deal with at full resolution, okay? Because then you need to have a window of plus or minus 32 pixels. But if you don't sample your picture, if you make it, if you lower the resolution, then this 32, pixel displacement becomes maybe only a 4 pixels displacement. Okay, so by looking at the lower resolution, then the search, the search region becomes much smaller. Okay, so 1 pixel at a lower resolution is basically a lot of pixels at the root resolution. So it is a typical thing where you start at the lowest possible resolution version of your image, you do a bit of a search, but only a few pixels back and forth. And then you propagate that results at level 1. Okay, so you multiply the displacement by 2, and you get candidate position for level 1. You do a bit of refinement at that level, and then you go back to level 0. Okay, so this kind of approach is still being used heavily. So the good thing with that is, like, at every single level, you only do a small search, plus or minus a few pixels. Okay, so it's pretty good. The problem, of course, is if you're looking at a very fine object here. Okay, so if you have something very thin, then when you downsample, that object might just disappear. Okay, so there's a problem, like, at the lowest level of your pyramid, you don't have all the information of the picture. You actually might lose some of these small objects. So that's kind of an issue, is how do you recover these objects at the intermediate levels. Anyway, so just some comparisons of the computations. I'll leave that to you to look into that. Anyway, I think we're going to stop here. Yeah, I don't think we'll have time. The next step is, all these things are kind of brute force approaches. Okay, we're actually going to look into that. One of the problems of using that is you don't get any what we call subpixelic displacement. So here, all the displacements, we say, let's find the nearest pixel in the next frame. Usually, the displacements are smaller than a pixel. Okay, the pixel is an artificial resolution we have in a picture. Okay, an object might move by an arbitrary small distance in real life. So maybe the displacement of that object corresponds, in fact, to a displacement of a tenth of a pixel, or a half of a pixel. And you'll be like, well, okay, you know, does it really matter? Well, the answer is yes. We can perceive motion up to, I don't know, a quarter of a pixel quite easily, maybe an eighth of a pixel. So if you do processing, if you do anything, and you stop at pixel accuracy, you will get pretty bad results. Okay, so you need to go to maybe at least a quarter of a pixel of accuracy, which, by the way, means that your search window now is 4 times bigger, and that means, like, you know, the amount of computation you have is way bigger. So next week we'll look into a little bit into gradient-based motion estimation, which is a way of doing Taylor expansion and so on, and to get a continuous, more like a Newton-based approach to the problem of finding what the best displacement. All right, that's it. So on Tuesday we'll actually have a lab on motion estimation, so I'll be able to play a bit with that. That's it.